Good afternoon. Welcome to this webinar. I'm Dave.
Hi there, my name is Ivar. Welcome.
Right. So today we have an interesting topic around base array deployments. Before we dive into that, I would like to highlight or mention that during the webinar you can leave questions in the Q&A tab. So please feel free to do that, and I will be happy to answer them at the end of the webinar. That being said, Ivar, base array deployments.
Yeah. Today we have our specialist in Sweden, Jürgen from Sweden. Hi, Jürgen.
Hi there.
Please introduce yourself a bit. Maybe people have already seen you in the previous webinar, maybe, but it's always good. You have quite some experience in base race, right?
Well, yeah. I mean, we started here at Bose for many years ago, and I started to work here in '94 as a sound system designer, and so doing church and stadium and helping rental partners to do their concert tours with the sound.
Yeah. You're our expert in base arrays, we can say. That being said, I think it's good. Let's say the stage is yours, Jürgen. So, are you ready, Jürgen?
Sure. I found a few photographs of different base arrays type from the early days, and as far as I know, one of the earliest design that we have done here at Bose was a J-Ray at Heysel Stadium in Belgium, installed in 1995. If you look really carefully behind the horn, you can see the J shape. It's a dual 18-inch subwoofers. Moving on, 2 years later, I found a really example of for a live tour in Sweden in 1997, where two 6 meters end fires were flying under the stage ceiling. Moving on to 2003, I found an early example of a compound array in an ice hockey arena, also in Sweden. And one of the last examples for this is a ring array that was installed in Sweden in 2008. So all the subs are mounted or installed in a ring in the middle of the cluster there. All these comes from an internal handbook written in 1998 by Chris Ickler from Acoustic Research here at Bose, who also became our mentor regards base arrays, actually until recently. And fun enough, there are features described in this handbook that is still not fully explored. In 2001, we filed a patent called modular base arraying that was later granted in 2004. So that's a little bit how it started and what different types we're usually working with. Let's move on to present time, and since many years back, I think the majority in the pro sound industry knows what a base array is. I've been watching many fantastic webinars lately describing how it works and even some great experimental new array configurations. And it's really a wonderful time when so many people share their work. So we decided to show you a use case instead of the theory behind it. And I will use ease focus. It's so easy to use, but we will start with a place to put a sound system in. The easiest way to do this when there is an outdoor gig is to use Google Maps. This is downtown Gothenburg in Sweden, and in the middle of the town there is a special place where they used to have concerts on this grass field. Usually the stage is located here, and the audience area is this grass field in front of the stage there. As we're going to use ease focus, it's easier when this stage is at the left of the window on your computer and the speakers are pointed to the right. Now there's a function in Google Map. If you click on this little globe here, you will get a compass, and with that compass, if you click and hold your mouse and just drag it, the drawings will rotate. doing that becomes much easier to use that in ease focus. The next thing you want to do is to measure a distance, so we can transfer this image to a drawing by right clicking and say measure distance. And the first click is the back of the room, and then where it says 0, if you just drag that to the front of the stage where you think it's going to be located. And I think it's going to be located somewhere here. I can still see that my image is a little bit not straight. So this is probably easier to work with. It's now straight in the horizontal, and we have measurements of 50 meters from the front of the stage to the back of the audience area. When this is done, we can use it as a drawing by the simplest ways to do a screen capture. I'm using something called Snagit. You can use whatever you want, and then you just save it as an image. And the next thing is to import that into Ease Focus. So I have launched Ease Focus, and I'm running the version 3.1.11 for your reference. So in here, the first thing we're going to do is to insert the drawing. And when that is done, we need to scale it and set it to a reference point. And that will be at the front of the stage where we position the point A. And point A will also be on X0 and Y0. So that is straight in the middle of the stage. And we also know from the measurement we took in Google Maps that the distance from point A to point B is 50 meters. When that is done, we have transferred our image to a drawing that is actually scaled. The next thing is to actually remove this first surface that is automatically inserted when you launch a program. And we will use another one, this one, which we will position in the front of the stage. So that will be X and Y 0. We know from the measurement that is the depth of it is 50 meters, the throw distance for the sound system. And we will also just make it a little bit bigger, and we will actually adjust these handles later on. The stage will be a stage line, probably an SL260, which is about, as far as I can remember, it's about 10 meters wide versus 7 meters deep. And of course, it's going to be positioned at X0 and Y0. I know that if you hoist it as maximum, will be 1.6 meters. And if we want to do some calculation on the stage, the musicians will of course be standing. And actually, I forgot to do that with the audience area as well. Right now, they are sitting. And we will calculate for standing people. So when this is done, we have a playground, more or less. The next thing is to insert a sound system by clicking on the sound source. And we're going to use Show Match from Bose, which is a rental system. And it's going to be positioned at X0. Y, the stage is about 10 meters on the stage floor, so about 5.5. That will just make room for that. The distance on the hanging point on the SL260, I believe, is 7.9 meters minus the chain motor. So the maximum height will then be 7.4. That's pretty well good. The system has a throw distance of 50 meters, and it's going to be used for pop rock music. So I will be using a 12 box array to do this. Now, when it comes to the system, with show match, they comes in a couple of different carts or transportation carts. There is a long throw and there is a medium throw and there is a downfield cart. Contains 4 modules in each. So obviously in the far field I will be using the SM5, which is a 5 degrees vertical with a 55 degrees horizontal waveguide. That is a far throw. So the first 4 module comes from that transportation card, and we'll do the far throw. And then in the middle part of the room, audience area, so this is this part here. This next section we will be using an SM5, so still 5 degrees vertical, but with a 70 degrees horizontal waveguide. And they are transported in a cart with 4 of them. The downfield we will be using 100 degrees in all, and in the bottom there is an SM10, so 10 degrees vertical and 100, and a 20 degrees vertical and 100 degrees waveguide. So that's the system. The next thing is to name it, so we can have good use for it. So this will be main stage, stage left, and the rigging will be that little one they call, it's a kind of a T-bar instead of the full frame. So let's splay it. I'm using the autosplay as a good starting function with the conventional algorithm, and of course the target area is just the main areas. When that is done, he has managed to find splay angles and pitch. Looking at the A-wedged broadband, this is a level, and as you can see, the slope is pretty okay. You may want to tweak a few splay angles in between here, manually maybe, but in general I would say this is a really good starting point. So this is the main stage left. All the filter settings we will be using here is at the crossover of 65 Hertz. So next thing is actually just to copy and put a second one, stage right, which will be located on X0 and -5.5. And of course this will be our stage right. There we go. Then we have a left and right system. And it's time to insert the subsystem. So I'm going to use a sub array and position them in the center. Now, as you can see, they ended up under the stage. So I will actually move them to X1. And because in the front of the stage there will be an area where people can't be. Maybe there are some evacuation area here. And so let's actually do that right away. So we're going to take like a 2 meter off the audience area. That will probably match that reality. Anyway, back to the subsystem. So the number of subunits is going to be equal to the number of full range module on each side. So let's do that. We have the 12 full range modules, so I will use 12, and we had 2 of them, so I will stack 2 subs. So in total I have 24 subwoofer modules. The spacing right now is 1 meter, and that kind of ended up nicely because it ends where the main array is. The next question is to find a proper coverage angle. And it can be a little bit difficult if we look at it by first turning off left and right. And just looking at the sub, and we select the 63 octave and turn on the mapping, and I guess I need to choose a lower resolution in order to speed it up a little bit. So right now it is at 77. Should it be at, 50, so less delay on the corner, so the coverage angle 50, should it be on 60? And in order to find the right coverage angle, I prefer to use one method, and that is to find this minus 6 dB point of the main array instead. So to find that, the 6 dB, minus 6 dB point is usually where you put a delay tower or something like that, a fill speaker in one another way. So knowing where the minus 6 dB point of the entire coverage or the entire seeding area is really handful, because then we can match the distribution of that. So let's turn off the sub and turn on the left and right. Switch to a wedged broadband and just look for that point. If we start in the back of the room, we can see that in the area here we have 105 dB. So the position you should look for at now is in the left corner, bottom corner right here. So when I move the mouse up again, you can see the level of the system. So we are running at 106 dB in the middle. That means that the minus 6 dB point should be roughly at 100. And actually, I managed to position that handle right actually that it was 100. So that's accidentally was good. The next one, if you look in the middle, it says 111 dB, 112 in the middle. So we are looking for 104 dB if we just move to the side. 106, 105. Okay, so we're a little bit too wide. If we move on to the front, 112, so 104. Okay, so we should probably be able to squeeze that in a little bit and search for 104. Okay, and moving to the middle again, 112 and straight up 104. Okay, so looking at this map, we probably have shaped the audience area where everything is in plus and minus 3 dB. So at the distribution, this is probably, if we set it to a 6 dB class width, right now we have about a 50% of coverage within the 6 dB class range. Now this will change if we move up to a medium mapping resolution. This might change a little bit. And it did. It moved up to 56%. So if we remember 56 and use that as a target to match the subwoofer coverage, I think we have a system that is kind of in good tonal balance. So let's turn off the main system, turn on the subwoofer, and get rid of the A-weighted filter, and just looking at 63 Hertz octave. Now we can see that the 6 dB width, or the plus minus 3 dB, the coverage at the 63 done by the subwoofer is 50% coverage. So we need a little more spreading than that. So let's start with 65 of the coverage angle, and that ended up as 51. So closing up 70, and you can see all these delay angles are changing. So it's spreading the energy better. 53%, 75%, and I will continue doing this until I hit the 56 percentages. 54, 80. Let's see what I end up with. 55.6, we're very close. Maybe 80 was the best option. Let's see what this ends up with. 56, almost on the same number. So that is how I do it when it comes to matching the coverage of the subwoofers. So I know that the spreading is the same in the sub range as it is in the full range So we have 56% from the main system, and we have 56% from the subsystem. So the next question is, what if we combine them? What will then happen? So let's turn them on. And the result when they are turned on is that it actually became less. We're down to 49%, and that's probably due to alignment of the main and subsystem. So, alignment. I've just made a new simple ease design here with the main, just a few modules and a stack and a position about 20 meters away. So looking at alignments, what's happening? It's a lot of discussions around the world how to measure and predict and what alignment actually it is. But you kind of think of it as beam steering. Alignment and beam steering is kind of the same thing. When you're looking at the third octave at the crossover point between the main system and the sub, this case it's 63 Hertz, you see that there's a build-up, a summation right in the middle of the main and the subsystem. So this is the beam, and that beam is actually where the highest SPL in the frequency is, and the purpose is to aim that beam down to the listeners, to the audience. It's kind of a pointing a speaker, exactly like this speaker. It's in between the main and the low. So one way to do it is to delay one of the pieces. If you delay the main system, this beam will steer up. We can just show you that. So if we go to the main system and delay that a little bit, let's say 1 milliseconds or 2, you can see that the lobe or the beam is starting to pointing upwards. If there is somebody sitting up here, good for him, bad for the others. So let's swing that back. So the beam always turn to this component that you are delaying. And we want to have the beam down to the audience area. That means that we need to switch to the sub and start delay the sub. So I want you to look at two things. One thing is the beam, which is of course now straight out here, and the frequency response at that position, and that is position number 1. You can see the level here. So when the beam starts to hit the listening position, you should see something happening here at the level. So that's just 1 millisecond. The beam started to tilt a little bit down. 2, you can see it starts rising at 80 Hertz, and the beam is probably slightly above him. So let's add another millisecond. Looks like the wavefront is really hitting him. Let's see if we can optimize it a little bit. Just look at the frequency response while I'm adding 4 millisecond. Right now he's probably slightly under. So let's say 3.5. Yeah, that added a tiny piece of extra energy at 63 Hertz. And you can see that the wavefront is actually hitting him. So aligning main and subsystem, at least in my perspective, is nothing else than just beam steering. And you need to delay the components in order to steer the beam to the audience area. So let's switch back to this design here, and we can see here at 63 Hertz 1 octave we have 3 beams. There's one beam pointing upward and there's one beam in the center. But that's how it looks on the top view. Let's look at the side view, and I selected the subwoofers, the array. That means that the side view is showing me the vertical distribution, and as you can see there is one beam going straight. Not straight, it's going upward at least, so we are playing for the birds, and we're missing the audience with that beam at least. If we switch over to, I just made a line here, we can see that this beam is not pointing upward, it's pointing downward. It's really close to a kind of a perfect pitch of that beam. So it would be nice if we can only adjust this beam, pitching that down, but we can't. So we have to find a good balance between those two beams in order to coverage and maximize the coverage. So switching over to distribution graph, we have this 49.8. We know from the vertical beam that they are pointing upward. That means that we need to delay the subwoofer if we want the beam to be steered down. So let's start by adding 1 millisecond to the base array, the broadside array. And from the picture, it became a little louder on the main beam, and we increased to 50.3. So let's add another 51.5, and you can kind of see that this beam is actually increasing in strength. Let's add another 52.6, and now it actually looks like we are stealing energy. Probably these beams here are going, they're becoming more pitched and more pitched the more we are delaying the sub array. So somewhere here we are going to steal too much of those beams and put that into the main beam in the middle, and that's what just happened. So we decreased the distribution down to 50.7 at 4 milliseconds. So let's let's switch back to the 3. So this is the highest number we can achieve, 52.6. Now, in order to double check this and see if this is correct, that we have took the right decisions, I put in some listeners. So if we switch over to frequency response, and to have a better resolution, we need to switch over to 3rd octave. And if we go back to 0, and just look at these frequency response. So these are all these positions here. And what we could expect if we are doing the right thing here, if we are delaying the right component, we should have higher SPL in the crossover bandpass. So let's go from 0 to 1. Okay, more or less all of them increased, so we are doing something right at least. 2, major part of them increased. There was a 1 or 2 that decreased. 3, all these guys were actually increasing. 4 millisecond. Now there was a lot of them that decreased. So by just clicking on these ones, on just looking at the frequency response, I would say that probably the highest number, the highest SPL in the crossover bandpass is probably 3 milliseconds. So that's my conclusion, that if the subsystems are located perfectly there and the mains are hanging right there, a 3 millisecond delay is a good starting point. Then I do the rest by measuring or by just listening. Now, what if the production tells us that they want to have much more people in the audience? They are going to open the stage side walls so people can be standing over here and looking into the stage. So for that you need, outfills, and you need the sub to cover a much wider area. So let's do that. First of all, we need another audience area, that's for sure. So, like they do on TV, I prepared a little bit. I made this audience area much bigger, and I added outfills to the systems. So they are covering this whole side sections. Looking at the coverage, and now I've turned off the sub, so this is just the direct A-wedged broadband. And looking at the distribution, we have a 73% within the 6 dB class width. So that's kind of our target, 73%, to try to figure out a good coverage from the subsystems. So first approach is to use left and right end fires. So I positioned 4 triple stacks after each other and delayed them according to a nice end fire. And they are pointing straight out into the audience area. The distribution is, if you click on it, it says 40.5%. So that is the coverage, and we had 73, so seems like we have a long way to go. By yawing end fires, so now they are yaw outward, and I play with the yaw angles in order to improve the coverage, and the numbers that I ended up with to be having the highest coverage or distribution here is when they are yawed 45 degrees outward. But still, it's just 43% within the 6 dB class width. So let's try another trick. So this time, I have stepped the end fires. So that means that this is a row of just stacked, because I wanted to keep the number of subs close to each example. So there are 4 in a row stacked, and then there is another 4 in a row, and they are using the same delay times, but as these 4s are positioned backward from the front of the stage, you can see that the energy, the beam is going in this direction. And the idea is to, same as when you yaw the entire end fire, is to make the whole system a little more directive and have a less overlap. So with this stepped array, we achieved a 46.8, which is better than the yaw end fire solution. So here is a vortex. If I zoom in on the ones, you see the stacks are one pointing forward to the side and to the other side. And this one, that little one, he is polarity reversed, and he is also delayed in order to maximize the power, at least in position 1 here, and also cancellate to this stage. It's called a vortex. And the result is actually worse than the stepped end fire. So we are down to 39 now. The last attempt I want to try is to see if we can spread the broadside, the center broadside array, to improve and see if we can find anything better than the 44%, which was the step array. So here is the broadside as we used before, but with this new bigger audience area. And it's still on 85 as we left it before, and it's actually better than the left-right solutions already by almost 10%. So let's see if we can improve this a little bit. Let's do it in big chunks here. 110, and we have a distribution of already 60. Wow, so this is much better. Let's step up to 130 degrees and see if we can beat 60 in any way. It's calculating, and there is 62.3. Now that's impressive. Another way to, I think this is probably the maximum. If we, just for the sake of it, increase it to 150, I think we are going to lose a lot of long throw capability, and yeah, we actually lost a few percent. So the maximum, or the most even coverage, is 130 degrees, which gave us a number of 62.3. The next thing you could do is also squeezing and changing the spacing. So now it's still on 1 meter. If we squeeze them a little bit into 0.9 instead, so remember 62.3, this could result in a little change. Yeah, so minor change into distribution. Looking at the levels at the side here, so you remember that you should look here in the left corner, 104 dB, and in the far back 106 dB. So that's pretty well. It's only 2 dB difference of a 50 meter throw distance compared to a much smaller. I think the length of this one is 17 meters, plus a few extra meters from the sub. So a really nice coverage, I would say. Do remember when you're playing with the spacing of the systems, is that if you squeeze them too close to each other, then all of a sudden they will start act differently, I would say. If you want to read more about that, there is an article called Mind the Gap. There's 2 parts of it that describes this phenomenon much in more depth. Very interesting reading. Right now, if you hold your shift key in ease focus, then you have a tape measurement, and you can measure the distance in between the boxes. With a 0.9 meter spacing, you have 20 centimeters or 0.2 meters in between the boxes, and you could play the minimum, and this is very unscientific, would be 15 centimeters. You should not have a smaller gap than that, to my experience at least. So read those articles and do mind the gaps. Do not make them closer than 15 centimeters. However, with 63.1 is probably the best coverage that I could achieve. It's only 2 dB difference from the side to the far back, and I think this concludes this wide coverage, this wide audience area, probably the most even low frequency distribution. So that concludes this session. Ivar and Dave, are you there?
Yes, we are, Jürgen. Thank you for this really detailed explanation. Really interesting, and we're going to check if there are any questions, so feel free. Do we have any questions, Dave?
So I don't see any. In the meantime, I was able to answer one of the questions, so that already moved to answered.
Yeah.
So
I
what
got,
on your end?
Yeah, some private questions. We got some. So please, if you have a question, put them in the Q&A, and I've got some private questions here. So we do got questions, Jürgen. How do the techniques shown in the presentation translate to indoor use?
Okay. Well, for indoor, I would say it's both easier and more difficult. It's easier as the reflection will help filling out the gaps, um, even that is from the diffuse field. So that enables you to use left-right subs and have still a good coverage with all that benefits. But at the same time, it's also more difficult, I would say, because directivity becomes a key component to sound quality due to the often longer reverberation times in the sub-range. So my kind of go-to design is a deep end fire at each side of the stage for indoor use.
Okay, thank you. One more. Do you have a go-to, let's say, a array deployment that usually works for an outdoor environment? So as a sort of rule of thumb, or is there maybe anything that you would not recommend for outdoor use?
Well, I mean, left-right creates a tight sound due to the shorter impulse responses, as all sub-signals arrives in a shorter time frame. That also left-right creates frequency-dependent streets with usually a drop-off -20, as we can see in the presentation there. Using a broadside, when that is correct deployed, it could be cover without any drops, but the penalty is a change in frequency response and also a loss in tightness. So I would like to think, what is the best for the audience? A little untied sub for all, or a tight sub but different frequency response for all. So my go-to would probably be thinking about the best for the audience, and I think that is having sub to all people, even that is not that tight as it would be in the left-right.
Yeah. Yeah, and that's maybe related to the next question that I have. Would you always design the array to make the low frequencies equally loud everywhere, or deliberately less for the audience in the back of the
Okay,
listening area?
yeah, it might look like that in the presentation, but in the perfect world, I would like to design for a constant frequency response throughout the audience area, but that is not so easy, especially when the subs are ground stacked on the ground. Usually the mid-high would get a natural distance drop, while the sub will drop more aggressively. In a few occasions, I actually added delay subs arrays in the back of audience to maintain their tonal balance. So I would say maintaining tonal balance is what I think is the goal, not looking too much to the levels. Getting the tonal balance is what I think is the optimum goal.
Yeah, this is also personal, of course, but
Yeah.
do you got some
Yes, so
questions in the meanwhile?
we have two questions popped in. So one from Winston. How accurate are these predictions when you get out into the field?
Well, as I said, the prediction only works if the system are positioned as they are in the simulation. For whatever reason they are moved due to security or something else that is moving, or you have something wrong. When I have compared using easeFocus, compare the results, the alignment time and such things to a real world when they are positioned as it is, it matches extremely well. I would say that is in a millisecond correctly. It's due to, at Bose we have a long legacy of measuring speakers for simulation softwares, and we use the same methods even if it's our in-house software called Modeler, where we also can listen to the system through an auralization unit, and that has been compared for so many years, and we are pretty good at doing the speaker files as good as they can possibly be. That means that the simulation from that on is, I wouldn't say easy, but it matches real well. So the answer to that question is yes. If you place them correctly, they will be incredibly close.
Good. That's good to hear.
Thanks, Jurgen.
More questions, Dave?
Yes, I just have a a question from Nitesh. Could you please share the East Focus session files with us? Is that possible, Jürgen?
Sure. Could you guys share my email, or how would you use that?
Yeah, so we could.
Dropped out. So can we go live back again? So big marker is failing now?
Yeah. Okay, just let's continue with the questions that we have here, Jürgen. So we have one additional question from Nitesh as well. Where can I find the East Focus GLL files for Bose show match?
So that is on our website, pro.bose.com, and you just click for the speaker. And we have, what I say, a big chunk of the speakers that we are producing, they are in a GLL format. If there isn't, you can't find it. So if you can find it, it is on our own webpage.
Okay.
Yeah, it's downloadable, right?
Yes.
Yes.
So
okay.
Then I will make sure, Jürgen, if you share us the East Focus design, we will make sure we make it available for the attendees in this webinar. So we will take care of that. Before we really end this webinar, I also would like to mention that in the handout section there are 2 documents available, so they're free to download. So please take a look there, as they might be useful as well.
Yeah.
Okay.
I think we're there.
Yes.
Sorry for the glitch.
Yes, our apologies for that.
Well, it's live, so sorry for that.
Things can happen.
I think we're good to go. If you have any questions, feel free, send us an email, and we are happy to help you with your questions.
And Jürgen, I would like to thank you a lot for attending this webinar.
Thank you.
Being with us.
And we hope to see you next week. Next week we have the STI webinar. So really interesting with our colleague Thomas in Germany. So hope to see you there. Stay safe. Bye-bye.